Normally, there are a lot of models, but some selected models I have taken here. That is, for example, first order linear time invariant systems, the second order linear time invariant system, port Hamiltonian LTI systems, and nonlinear systems, etc. We restrict our this presentation or discussion today to first order LTI systems. We would restrict ourselves, although the first order linear LTI system, because most of the models that can be written in first order form can be handled by the reduction techniques from numerical mathematics and systems and control. Then question rises, why model order reduction? Right. In principle, if the system order or dimension is too high, it may create difficulty in, for example, in simulation. If system order is too high, a simulation becomes time consuming or even impossible due to limited working memory. Then it creates difficulty in control. For example, if the order is very high, it has disadvantages for complexity. If the order of the plant is high, the control design becomes the more complicated and more non-transparent. Then computation time. The calculation of the control input could take longer than the sampling time allowed. This may lead to reduced control quality and even to instabilities. Then the hardware. The higher the order of the controller, the more powerful hardware is needed. Then it may also create difficulty in optimization. For each optimization step and each parameter update, the output to be optimized must be recalculated and may need larger number of simulations to converge. You all must have experience of all these things. Then again, the question is, from where do large models come from? The spatial discretization of partial differential equations using, for example, the finite element method, or say finite difference method, or finite volume method, the large number of large order of partial differential equations appear. Microelectromechanical MEMS or structural mechanics and heat conduction, etc. are some of the examples of this. Then modeling of technical system consisting of large number of individual components. For example, most prominent example is integrated circuits with a high degree of integration. VLSI, you all know, with hundreds of thousands of millions of transistors. So they create a system which has very large dimension, and the model order reduction becomes inevitable in these circumstances. Then what are goals of the model order reduction? In general, the goal of model order reduction is to replace a higher order system by another model that preserves the desired characteristic with lower complexity. Say, for example, what we understand by good approximation. The reduction technique should yield a reduced order model which captures the most dominant dynamics and well approximates the state vector or input output behavior of the higher order system, either in time or frequency domain. Hello?
Excuse me, sir. Sir, it's still at slide number 1 is visible. Have you moved the slide?
No, I have moved the slide. Is it not appearing?
Yes, sir. Actually, we are at slide number 1.
Slide number 1 only. I have moved to
Yes,
6,
yes,
7 slide. Let me check it.
Yes.
Good.
Yes, sir. Now it is moving.
फिर से शुरू करो. This you have seen?
Yes, sir. Yes, sir. Sir, please make it full screen.
You will just roll on.
Okay, sir. Okay.
Slides I will roll on because I have already. Yes.
Right. Right.
This you have seen. Hello.
Yes, sir. Slide number 1 is now visible.
This is slide number 1.
Yes, sir. Again, it is at number 1.
This is slide number 1.
Yes, sir.
Are you able to see this? Slide number 2. Hello?
No, sir. No, sir.
What is going on?
Yeah. Yeah. Window.
और जो मतलब वो स्लाइड शो मोड में जा रहा है वो तो शेयर नहीं हो रहा है, इसलिए उसमें चेंज भी नहीं दिखा रहा है.
So window share करना चाहिए.
तो दोबारा से शेयरिंग करके और स्लाइड शो वाला जो विंडो है फुल स्क्रीन वाला वो शेयर करके.
Sir, please reshare it. बस.
हेलो क्या कह रहा है अवधेश? व्हाट इज सेइंग?
सर कल इसको रीशेयर कर लीजिए सर एक बार से ना.
अच्छा अच्छा अच्छा. ओके.
स्लाइड को रीशेयर करके और स्लाइड मोड में फिर उसको कर.
कह रही हूँ स्लाइड्स में लेकर इसको रीशेयर करके फिर करो.
स्लाइड शो कर देते तो दो आने लगता है अलग अलग. ये वाला करने से किया वो चेंज कर रहा है
उसमें. हाँ, उसमें नहीं. राइट राइट. Yes, sir. Visible now.
हेलो.
Yes, sir. Visible now.
अभी आर यू एबल टू सी नेक्स्ट स्लाइड?
Yes, it is visible. Just move to the another slide so that we can see the lights are moving or not.
Are slides moving? Have you are able to see this slide, which is a modified nodal analysis examples?
No, sir.
It is going on.
कैन यू शेयर योर स्क्रीन. एक्चुअली सर आपने विंडो शेयर किया है स्लाइड शो का पावर पॉइंट का, इसलिए मतलब वो मूविंग वाला दिख नहीं रहा है.
हेलो. हेलो.
Window. Window share करके screen share करने स्पीड आती तो.
हेलो.
Yes, sir.
Yes, sir.
कुछ हमने are you able to now see the slides?
The slide is visible, but it's not moving, sir.
No.
सर
Goals
जब आप
of
शेयर मोड में तो आपको स्क्रीन और विंडो होगा, तो प्रोबब्ली आपने विंडो शेयर किया है, स्क्रीन शेयर कर लीजिए.
अच्छा
और उसके बाद
अच्छा अच्छा स्क्रीन शेयर किया है कि नहीं, विंडो शेयर किया है.
हाँ राइट राइट राइट. तो इसमें तो मल्टीपल हो जाएगा.
स्लाइड शो वाला
यस. Screen, if it is screen share, then there's no problem. Yes, sir. Now it is fine. Uh, Goals are MOR. So this 6 as a slide number. Yes, sir. Now it is fine.
Hello.
Yes, sir. Now it is
Are you
fine,
at?
sir.
Okay,
Yes, sir.
okay.
You can see the movement of this slide.
Hello.
Yes, sir.
Now it is seen. So I just roll down the slides, sir. Okay.
Yes, sir. It is rolling. It is now rolling.
Sir, I have already spoken about what are the motivating examples. So this is a MEMS device which has very large number of order, so that there is a necessity to use model order reduction. Some of the model order reduction to reduce the order of this electromechanical system to have design and analysis. Similarly, there is a solar panel which has very high order, and again we'll have to reduce this. Then third example is the large drive and machines. These are motivating examples why people have gone for model order reduction. The order is very high, it is in thousands. So we'll have to go for model order reduction in this case also. There is another example of modified nodal analysis in which the order is nearly 10,000 for MNA5, and then this is also reduced to a smaller order so that better understanding can be made. Now, what is model order reduction? You all know that it is we try to reduce the higher order system to a lower order model, which produces an output similar to the original with the same input. Then which models are reduced? The first order linear time invariant, second order linear time element, port Hamiltonian LTI system, and nonlinear systems, etc. are normally reduced. We later on discuss about it. But we'll restrict ourselves in this presentation, as mostly we'll restrict ourselves to this in this presentation for first order LTI system. The question is why we go for first order LTI systems only, or why we go for LTI system normally, why we do not go for other systems like non-linear systems. Because most of the model iteration techniques which are developed are basically applied to linear systems, and we can always with not to that extent a precision, we can convert all non-linear system to linear systems. So it is better to go for developing model regression techniques for linear systems, although the research is going on for applying model order reduction to nonlinear system itself. Model order reduction, we do it. I have already spoken that the higher order systems create difficulties in simulation. If the order of the system is too high, the simulation becomes very time consuming. In the control also, complexity, computation time, hardware requirement, etc. are very intensive in terms of cost, and very powerful hardware would be needed if we are having a higher order model. Then optimization, the number of iterations required would be very large, and it would always be recalculated every step if the order is very large. So it requires large number of memory, etc. Then where these higher order models come from? So if we do discretization of partial differential equations, we find, for example, in case of using finite element method or finite difference method or finite volume method, etc. In the MEMS or structural mechanics or heat conduction, we find that the order of the partial differential equation is very high, and it necessitates, in fact, that the order of the system is reduced. Then another example is VLSI, That is the modeling of technical system consisting of large number of individual components. And this has hundreds of thousands of millions of transistors. So again, these create or generate a large number of or higher order models. What is the goal? What are the goals of model order reduction? In general, goal of model order reduction is to replace an existing higher order system by another model which preserves desired characteristics with lower complexity. Right? What are the requirements? It must have a good approximation. What we mean by good approximation? Good approximation means the reduction technique should yield a reduced order model which captures the most dominant dynamics and will approximate the state vector or input-output behavior of the higher order system, either in time or in frequency domain. Then it must preserve the system properties. Right. Basic features of the original model, for example, stability, say passivity, structure, realizability, etc. It should be preserved in the reduced order model. Then it should be numerically efficient also. What we mean by numerically efficient? It means the reduction method should be as numerically efficient and as stable as far as possible. It should not be expensive offline, and especially online computation should be avoided. That is, inverse of matrices, etc. The model reduction method must be such that it avoids matrix inversion like this. So there are various ways to derive such a reduced order model, and there are several possibilities for classifying these approaches. One may classify model order reduction approaches into projection and non-truncation based techniques, projection or non-projection based techniques or truncation based techniques, or into frequency domain and non-domain time domain methods. But it's not actually any sharp line of division between these. Say, for example, we later on see that a time domain technique known as the Krylov subspace technique, it is an implicit parity approximation. If we go for explicit parity approximation, it becomes a frequency domain technique. So people have themselves have divided or classified. Different classifications have been made. We'll do it based on our own this classification. We'll be doing projection based and truncation based techniques, right? So now we come to system modeling. If we say, sometimes some of the authors have said that the non-truncation based techniques are frequency domain techniques. Truncation based techniques are frequency domain techniques and projection based techniques are time domain techniques. So if we go for frequency domain approach, you all know that the transfer function can be represented as given. The AIs are the numerator parameters and BI are the denominator parameters, and time domain approach is represented by state space, where first equation represents the state equation, the next is the output equation X, and they are represent the real matrices of order n. If P is the output, then the order of there will be P outputs and there will be M inputs. U is the input to the system. Then system may also be represented in implicit state space representation form as shown in this equation, where E may be singular. We assume E to be symmetric and positive, definite or semi-definite, and is called the descriptor matrix. AE have order. If we have chosen higher order as n cross n, n, then A and E would be of n cross n, B will be n cross m, where m is the input and D would be P cross M. Normally we assume D is equal to 0. And transfer function can be obtained, you all know, by taking Laplace transform of the above equation under condition that x0 is equal to 0, that is initial conditions are not existing. So in frequency domain, the transfer function, if we start with the frequency domain methods, in the frequency domain, the transfer function is given like this, GS, and the reduced order transfer function is given by G cap S. Domain, these are represented by these equations, and reduced order model is represented by these equations, right? There are different approaches. Frequency domain or non-projection based, as I already told you, which includes Pade approximation, Routh-Pade approximation, then pole detention or pole clustering, and method based on IC minimization by applying conventional or evolutionary techniques. Then time domain or projection based, as I've already told you, this is not a, I mean, this can be changed. Time domain techniques can be overlapped with frequency domain technique, or frequency domain techniques can overlap with time domain or projection based techniques, right? So Krylov subspace method, balanced truncation method, proper orthogonal decomposition method, or modal truncation. We'll discuss these methods, I mean the projection based method more, and what we'll do is that we'll discuss Pade approximation and Routh-Pade approximation, try to see one example also, and we'll do Krylov subspace method in detail, and then we'll if time permits, then we'll go for balanced truncation, proper orthogonal decomposition, and modal truncation methods. And then there are methods which we call as variants of above, because there are methods, we call it as hybrid methods, where we are combining say pole detention and Pade, we are combining pole detention and Routh-Pade approximation. Similarly, we are combining Krylov subspace and balanced truncation method. We are extending Krylov subspace method, which is normally used for linear system, to nonlinear systems also. Proper orthogonal decomposition method is basically for non-linear system. Similarly, model truncation method we can use. So there are combination of these methods also, and research is going on developing better and better model reduction technique by combining. Time and frequency domain methods are also combined. Later on, we'll see it if time permits. So we'll discuss this Pade approximation first. The Pade approximation is the best approximation method people say of a function by a rational function of a given order. It was developed by Henry Pade. I have because we have already wasted some time, so I have not done the historical development of model order reduction technique, how it was initiated few decades back. This Pade approximation was developed by Henry Pade, and it takes into account the coefficient of Taylor series expansion, and the series is truncated at certain chosen order, and then we are able to determine the low order model. So suppose this in frequency domain, the G is represented by this. Now if we expand this transfer function in power series about S is equal to 0, then we get these coefficient T0, T1, T2, T3, etc. It's an infinite series, and we truncate this depending upon the chosen order of the reduced order model. Now if G cap S is the reduced order model, transfer function of the reduced order model, then it is again expanded in power series. Then we get these time moments of the reduced order model. In the Faraday approximation, what we do is that suppose R is the reduced order, this order of the reduced order model. Then 2 are terms of the power series expansion coefficients of system and models are matched. For example, if we choose the order of the second order, the order of the reduced order model as 2, that is R is equal to 2, then twice R terms would be matched of the system and reduced order model. So twice R means 4 terms will be matched. That is T0 will be equal to T0 cap, or T1 cap will be equal to T1 cap, T2 cap will be equal to T2 cap, and T3 dash cap will be equal to T3. So if we match these, we'll be able to determine the reduced order model by solving these equations. Now if we expand this transfer function around s is equal to infinity, then these are the terms m0, m1, m2, etc. These are called Markov parameters. In fact, if you apply the final value theorem to GS, that is t tends to infinity or s tends to 0, we will find that the remaining term will be a0 by b0, right? So in the Faraday approximation, this T0 is also A0 by B0. If you expand this transfer function in power series, then you'll find that the first time moment comes out to be A0 by B0. That is, if you match time moment only, then the matching of, it says that s is equal to 0 or t tends to infinity. So the steady state matching of the system is better in case of if we are matching only time moments. Now people have thought of that if you also include, say, some terms, say, applying initial value theorem, then in that case we found that initial matching is better. So what people have done is that they have combined time moments and Markov parameter. For example, if we have to reduce the system to second order, then 2R means 4 terms will be matched. Then we can match 2 time moments, 1 Markov parameter, 1 Markov parameter, 3 time moments, and so on. And the combination chosen will depend upon the experience of the user, how many time moments and how many Markov parameters will be used. But I tell you, it is still under research that what type of system, in what type of systems, how many time moments and how many Markov parameters will be matched. This is under research these days, that how to choose time moment and Markov parameters for a particular system. So if we go for this, then we'll have to go this M caps, MI caps are also representing the Markov parameters, and we can choose the different number of time moments and Markov parameter and get a combination of time moment and Markov parameters matching, and then we can get a better overall time response approximation. So as I have told you, TI and MI are the time moments and Markov parameters, MIRs. Then these equations we get. A0 is equal to T0 B0. This is A0 cap. So what will be the first time moment? It will be A0 by B0. What will be the second time moment? T1. T1 will be A1 minus this T0 B1 over B0. So what in Faraday approximation is done is that, say, for I'm considering R is equal to 2, so I have written 4 equation, but it will go to infinite number of equation because the power series is infinite. So if we are having 4 equation, R is equal to 2, then these will be the 4 equations. What we do is that we from the last two equations, right? From the last two equations, we can, in fact, it is an infinite series, so it is written as A2, A3, and so on. Otherwise, if we are considering 4 R is equal to 2 and we are matching 2 R terms, then will be 4 equations. Say, for example, A0 is equal to T0, B0, and suppose we take Markov parameters also. So the Markov parameter equation will be A0 cap will be equal to M0. Similarly, A1 cap will be T0, B1, T1, B0 cap, and so on. Similarly, the fourth equation for Markov parameter will be A1, M1, M0, then M1, B0. So what I am trying to say you that in 4 equations which we'll get from the last 2 equations, we can eliminate this. We'll be able to eliminate this numerator coefficients, and last 2 equations will be only in the denominator coefficients, right? So what we do is that first we determine the coefficients of denominator polynomial in Paddy approximation from the last R equations. Once we get the denominator coefficients from the last R equations, that is B1 dash, B2 dash, or Bi dash are known, then we determine the numerator coefficients by first R equations. In fact, if a chalkboard would have been there, I could have done it on the chalkboard. It would have been more clear, because when I'm writing here, I'm writing the general equations. But for a particular example, if you do it, you will be able to eliminate the from last R equation the numerator coefficients. And once you determine the denominator coefficients from the last R equations, you are able to determine the from the first R equation the numerator coefficients, and you are able to determine the reduced order model. So our aim is to determine this A0 cap, A1 dash, A2 dash, and B0 dash, B1 cap, and B2 cap, right? If it is a second order model, then A0 dash, A0 cap, A1 dash S, and A2 dash, A1 dash S, and in the denominator we'll be getting S square plus B2 dash, B1 dash, right? So if we are this, we can eliminate this denominator coefficient B2 dash by dividing numerator and denominator by B2, and we are having only 2 coefficients in the denominator and then 2 coefficients in the numerator, and then we can, once we have determined the BI's, we can determine the numerator coefficient AI's by making use of the first R equations. These first R equations, right? Then in this Paddy approximation, there is no constraints or restrictions on the coefficients of the denominator polynomial. They can take any values. It can be positive or negative, right? So stability is not guaranteed in case of Paddy approximation. That is what happens, that although the original system is stable, but sometimes we find that this reduced order model turns out to be unstable, right? So what the people have done is that they have used techniques which can guarantee stability of the reduced order model. And the foremost technique was Routh-Paddy approximation, in which the denominator of the reduced order model was obtained using Routh table, and then numerator was obtained using Paddy approximation. So together this technique is known as the Routh-Paddy approximation. If we have determined denominator using Routh approximation, then it is guaranteed that the reduced order model would be stable. And Paddy approximation is used for determining the numerator, this coefficients. But the better approximation would turn out only when we match two R coefficients. Keep in mind that a better approximate would be when we match two R coefficient, because in paired approximation two R coefficients are matched. But for guaranteeing stability, we have restricted or reduced to the matching of only R terms, because denominator is determined by Routh approximation. There is no matching of power series expansion coefficient for determining denominator. So the reduced order model, which was obtained using Routh-Padday approximation, although it guaranteed stability, but it did not match. I mean, the reduced order model was not overall better in terms of matching of time response or frequency response. So the research started how to get a better overall time response approximation, in which we are able to match or near match more than R terms. At the same time, we can guarantee stability. So there are papers, I'll give you in reference. I have not included in my presentation that paper that uses some optimization method. The paper is published in IEEE Transaction. Adhesh might be knowing it. And then in that, optimization is used. So in fact, in that there is no perfect matching of time, moment and Markov parameter for determining the coefficients of the denominator polynomial. They have constructed this optimization function, and they have minimized that optimization function and putting some restriction or constraint for stability. So it matches or near matches two R terms, and it guarantees stability also. So this is what is written here. So in this, we have taken one example. The higher order is a fourth order system. We have found a reduced order model using Routh approximation method, right? Time response, which we have plotted. The model 2 in fact represents the Padday approximation, and this model, this one represents Routh approximation. We find that model 1 has a better matching to this. In fact, in earlier researches, the Padday approximation sometimes gave better approximation. People find that even if we are not including Markov parameter, we are including only time moments, but the overall time response is better. Initial matching is also better, and the steady state matching is also better. So then they have tried to calculate the time moments and Markov parameters of system and models. So they found that in certain cases, even though the time moment is matched, the Markov parameter automatically is matched. So only by matching time moments we are able to get matching of Markov parameter itself. So sometimes if a Padday approximation is getting a better overall time response approximation, we should not discard the concept that Markov parameter may not be matched. In certain examples, matching of Markov parameter automatically takes place, so that people can go ahead with matching only time moments. Then in frequency domain, there are what I was trying to tell you, the optimization based methods are also there, existing there. Coefficients of numerator and denominator of the reduced order model can be obtained by minimizing the ISE by conventional or evolutionary algorithm methods. So if GS is the transfer function of the system, and YS is the response, and GS is the G cap S is the transfer function of the reduced order model, and YS is the Y cap is the response. Then IS can be it is probably that is missing. Slide is missing probably. So we can find this ISC by taking integral square error of this GS and G dash S and minimize that error, then we can get the reduced order model. The optimization tools which are available, they are conventional optimization tools like Luce-Jacola algorithm, geometric programming, linear programming, non-linear programming. Then some meta-heuristic methods like particle swarm optimization, genetic algorithm, differential evolution, ant colony optimization, artificial bee colony optimization, and so on. There are other methods also, cuckoo search algorithm. So you can all use that. We have taken an example of this. This was an 8th order system. By applying Luce-Jacola algorithm, we have found this approximate. So you can try yourself by using some other optimization algorithm and check how the response you are getting, whether it is closer to the original system or not, right? Then as I told you, there are projection based model order reduction methods. Kraloff's subspace method is a very popular method because it can reduce thousands and thousands of higher order system to a reduced order model. Then we'll discuss this Kraloff subspace method. This Kraloff subspace method, in the Kraloff subspace method to find model order reduction, we again go for expansion of transfer function, power series expansion of transfer function. Right, as I have earlier told you that there is a overlapping of methods, classification of methods. In Kraloff subspace method also we mass time moments and Markov parameter, but it is a reduction by projection. A higher order subspace is projected over a lower order subspace, right? And then we are able to determine a reduced order model. So, for example, we are representing this equation. Normally what happens that we are using a descriptor equation, descriptor type of equation, where E is there also, but for simplicity and just to reduce complexity over a screen, I have taken this state equations only. So original system is given by x dot is equal to ax plus b and y is equal to c transpose x. We are making this projection, right? That is x is equal to u r x cap t. Now if you substitute this in the state equation, you will find that you are getting this equation, right? This is what we do in the projection. We consider a projection like x is equal to u r x cap t, and we substitute there in the R. So what we are doing, we are projecting a higher order subspace into a lower dimensional subspace. We'll see that there are, if R is the order of the reduced order model, then this A matrix, in fact this A matrix would be A cap. There could be some mistyping. This is A cap, we'll later on see. This order of this A is very, very less than the, depending upon the choice of the order, right? So this is a VRT-AUR. This is in fact A cap, right? In the second equation, we are getting VR transpose AUR. This is A cap. VR transpose B is B cap. So this is having a very small order, right? Here this we choose such that this transpose turns out to be the identity matrix. Remember, we are trying to find this, what is Krylov subspace method. Here we have represented this, what I was saying. Ultimately, we will be getting this A cap, where A cap will be equal to C transpose UR, and A will be there, and then B cap is equal to this. These are certain manipulations which we get in the Krylov subspace. We are omitting this is, in fact, this we are getting this span BE square B, which is the for it, this we are doing for single input, single output system, and these, for finding this, there are algorithms known as the Langkos and Arnoldi algorithms, right? So results are given here. Then we can later on find yourself. You can find how they are derived. This K span, the span of this, how this represents the Krylov subspace method, right? This is in fact the representation of. So what we'll do is that depending upon the order which we have chosen and the projection, this K capital EB represents the EV you can have, or you can replace it if you are not using descriptor method. I have written this because mostly we are using descriptor method. So this will be in fact notation for it, and then we'll be getting this span of this. With this equation, we'll be able to determine the reduced order model. Right. So if you remember in the Padday approximation, if you have done it, we can expand the transfer function in Taylor series about single point, or we can expand it around multiple points, right? So in this particular slide, the comparison is made that if we are having multiple input points, then we are getting a better approximation. HS is this line, this red line is given for the system, and the dotted line is given. So for multiple points, if we choose, that is, we can choose, instead of choosing s is equal to 0 or s is equal to infinity, we can choose s is equal to a1, s is equal to a2, s is equal to a3, and so on. We can expand the system into Taylor series. Using Taylor series method, we can expand the system, and then we can have matching of this. So we have found that if we are having multiple expansion points, we can get better results. So once again, if you are getting a better result choosing single point, or s is equal to 0 and s is equal to infinity, doesn't mean that we have to only go for multiple expansion points. We can use that also, but if you do analysis, the sum of the points automatically get matched, right? So we have got a comparison of Padday approximation with Krylov subspace method. In this figure, we have taken one example and we have found that Krylov subspace method is giving better approximation, right? So, in nutshell, what we were trying to see is that there are two possibilities. Either we can do this in expansion, this frequency domain or time domain, right? Or alternatively, we may say that truncation based method or projection based methods, right? In the projection based method, we are having this Krylov subspace method. In fact, we'll have to take another set of slides. That is why I have stopped here. Then in the Krylov subspace method, we are projecting this higher order subspace into a lower dimensional subspace. Then there are proper orthogonal decomposition method. In the proper orthogonal decomposition method, while in the Krylov approaches, are based on matrices on itself, the method of proper orthogonal decomposition is based on trajectory xt, that is the outcome of the system. Right, this method essentially, I'm just speaking of because time is short. This method essentially constructs an orthogonal projection basis from the orthogonalized snapshots, right, and which are obtained during the training point. After obtaining the projection matrix from the proper orthogonal decomposition approaches, the reduced order model are generated. Then how to choose these choosing snap points? We, in the most common type of choice is time snapshots. Of that, the transient response are collected in data matrix, and then we are able to find the reduced order model. Then there is another method known as the truncated balance realization. Just wait. We are stuck up with this, in fact. Avdesh? Hello?
Yes, yes, sir. Yes, sir.
ये स्लाइड जो है आगे नहीं बढ़ पड़ी, इसका बीच में एकदम से जो स्लाइड्स थी ना वो थैंक्स करके आ गया। मैं देख
जी 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 31
देख
पे है
हैं,
31 स्लाइड नंबर 31 पे है और 32
हाँ 32 एकदम से वो आ गया, बीच में और स्लाइड्स थी। एक मिनट में चेक कर ले रहा हूँ नंबर, तो वो जैसे स्लाइड्स 32 एकदम से आगे, लगता है कॉपी नहीं हो पाया क्या इसमें,
राइट,
फिर मैं चेक कर लूँ एक मिनट
जी। आज पानी नहीं है।
उसको
Sir, now it is visible. Balance truncation.
Actually, Avdesh, what has happened, I have transferred those slides to another slides, which normally could not be. So I'll have to go back for. So this balance truncation is visible. Hello?
Yes, yes,
Okay.
it's visible.
So in the balance truncation also, this we have done it for, the projection based method we were continuing. We have done for this Kralov method. Then another projection based method is truncated balance realization or balanced truncation method. In this this is one of the alternative methods for model order reduction of this linear time invariant system. In this method is basically based on singular value decomposition. In fact, one has to understand what is singular value decomposition first. Then we will be able to appreciate more this method then. But how we are doing it, let us again, we are having this type of transformation, x is equal to t x cap, and I think how to determine how these eigenvalues and singular values are found out. So if you do this transformation, we'll be able to get this, and there are some terms like observability gradients, then controllability gradients, etc. A lot of mathematics are involved. So what we have to do is that we'll have to determine the controllability and observability gradients, and we can, using these equations, similar equation is for controllability gradient also, right? So WC represents the controllability gradient and WO represents the observability gradient, and then finally we are able to combine this. Escaping some of the slides. How balancing is done, and in fact it's so mathematical. I personally feel that it is may not be very clear to the audience how we are going to do it. So what happens, we have determined the singular values and then we have used these equations to find this. So there is some mathematical manipulations. Ultimately, will be able to obtain these equations. So if you do these manipulation, you find that the original eigenvectors change, and by so ultimately we will be able to get the reduced order model. So I come back to this slide, how we have obtained this. So WC and WO, in fact WC is the controllability gradient and WO is the observability gradient, And with the help of these two gradients, we are able to determine the reduced order model. And that matrix which we get is such that we are able to divide it into strong subsystems and weak subsystems. And the weak subsystems are omitted, and we finally get the reduced order model. Avdesh? Hello?
Yes, sir.
एक मिनट जरा से स्लाइड्स कुछ ओवरलैप हुई चली जा रही, कुछ प्रॉपर्ली वो नहीं हो रही जरा सा
मूव कर रही है सर, तो एनिमेशन की वजह से हो रहा होगा सर, 1 by 1 आ रही है।
हेलो?
यस सर।
हेलो?
यस सर, यस सर।
अभी क्या है, आई कैन जस्ट ऐसे ब्रीफ कर दे रहे हैं
जी।
सो वंस वी हैव we say that we have what we'll be doing. In fact, once we have found that there are two methods, I mean there are two classification, frequency and domain method, time domain method, or projection based method or truncation based method, and we know how to reduce the model. So the best thing would be to discuss, in fact, what are the drawbacks for researchers, what are the drawbacks, and what would be the future scope of these reduced order models which we have so far discussed. So the Krylov subspace method is numerically efficient since no expensive calculations are necessary here. The moment matching procedure implicitly performs a pad expansion around the expansion point, thus leading to a very accurate model. However, the stability and passivity of reduced order model is not guaranteed in pad approximation, even though the original system is stable and passive. Moreover, there are no efficiently computable error bounds for the approximation quality, right? The reduction procedure in Krylov model or the reduction method is partially automatic. However, the computational procedure in moment matching becomes fully automatic as soon as the choice is specified for the expansion points. So I mean, when we talk of what were the goals, then we wanted a good approximation. The good approximation means that the reduction procedure should be computationally less time consuming, and it should be automatic also. But Krylov subspace method is, will have to intercept once you give to the computer some initial values. This Krylov subspace method gives you the reduced order model. So it becomes fully automatic when we combine it with the pad approximation or some intercepts, interventions into this method. These things are under research these days, how to convert this moment matching, which is fully automatic, to a Krylov subspace method and so on. So there are some algorithms. The Krylov subspace method, since it depends upon the matching of time, moment and Markov parameters, so initially did not give stable this reduced order model like pad approximation. But there are methods which have been developed like iterative SVD rational Krylov algorithm, which is known as the ISRK, which combines a singular value decomposition based method and balanced truncation method with the Krylov method. Then it preserves stability and this passivity also. The main advantage of this truncated balance method is that the reduced order model is also balanced and a minimal realization. The stability is preserved in the reduced order model. Right? It is well known that only balanced truncation method is fully automatic when a requirement on quality of the reduced order model is given. Right? The existence a priori knowledge of bound allows the automatic choice of reduced order model. So those who are working in the area of reduced order model, they must be knowing that what should be the choice of the order of the reduced order model can also be determined using TBR, because we make use of we write the matrix in such a way that the important singular values are in one place and lesser important are another place, and we are able to truncate them. There are some extensions and adjustments of the high dimensional sparse model. For example, low rank alternating direction implicit LRADI and the rational Krylov subspace method. These are new developments and they both are very closely related to Krylov subspace method. Right? So similarly, the proper orthogonal decomposition techniques, they are used mainly for non-linear systems. Since the technique is quite generally applicable, which is biggest advantage. The method has two big disadvantages. Firstly, the first disadvantage is that it requires the calculation of a large set of snapshots, thus the necessity to run many calculations on HOA, higher order model. Secondly, the accuracy of the resulting reduced order model is generally not known. So I'll send these discussions to the coordinator, which will be circulated later, because I was discussing in fact what would be the future scope for model order reduction, right? So one of the basic future scope would be to develop an improved subspace space method, right? Krylov subspace method or projection space method, projective subspace method. So there are ample opportunity to develop or possibility to develop an improved method by combining various methods or using different algorithm as such. Then second is to extend the model order reduction method to interval and fractional order systems. I think you must be aware that uncertain systems are there, and how to extend the model. Suppose we develop a model order reduction method, then how it can be extended or applied to interval systems and fractional order systems also. It is sometimes necessary, while approximating a stable model, that the reduced order model is also stable. In many systems, the coefficients are constant but uncertain within a finite bound, as we have seen in this Krylov subspace method. Such methods are classified as interval systems. On the other hand, the system dynamics of some systems include non-integer differential or integral operators. These are known as the fractional order system. So it is better if you develop a reduced order model, then you can extend it to application to fractional order system and also uncertain system. Then it would be also interesting to find out whether your method can be extended to be applied to non-linear systems also or not, or it is only valid for linear systems. So if it is, let's say for example, the Krylov subspace method can be extended to non-linear systems as well as bilinear systems, right? So it will be better to develop a method, model order reduction method, which can be extended. Suppose we have developed it for a linear system, then you can develop it for a non-linear system, or whether it can be extended to be applied to non-linear systems and interval systems or not. Then whether we can design, ultimately our aim would be to design controllers for systems. So whether your model reduction method can be used to design controllers and suboptimal controllers or not. Traditionally, for designing optimal control law, the state feedback gain matrix is computed by solving, you all know that, by solving Riccati equation, which is primarily obtained using calculus of variation or Hamilton-Jacobi-Bellman based equation. So whether the method you develop can be used to design an optimal or suboptimal controllers or not. So there are papers in which Krylov subspace method is used to design a suboptimal controller and optimal control. What basically people do is that the higher order system is given, you have to design controller for this. Then you reduce the order of the system and then design controller or control law for this reduced order system. And then you apply this reduced order system or controller which you have designed to a higher order system, right? And the papers are there which say that this way of designing optimal and suboptimal controller gives a better approximation. So then another important area is how to determine the optimal order of the reduced order model. So this singular value decomposition and this balanced truncation gives some idea of how to choose the order of reduced order model, but there is still scope for research into find what will be the optimal order of the reduced order model, because it is an important issue. Otherwise, overestimating the order of the reduced order model can significantly exceed the computational cost. So we'll definitely like to explore the possibility of developing an algorithm for finding the appropriate order of the reduced order model. Now, as I have told you in the beginning, that the reduced order models or the algorithm which are developed are customized for different applications. So there is possibility of searching new areas where you can apply reduced order modeling. I have recently found that these are applied in biomedical systems, they are applied in biomolecular systems, they are applied in civil engineering also. They are applied in acoustic system, vibroacoustic systems also. So you can also go for applying your model order reduction technique which you have developed to different systems also. You can use them as a case studies, and these are being used in power systems also. So different techniques can be developed, or model order reduction techniques can be developed which can be applied to different systems. So this I would like to stop here. I am not very sure because in between there was some overlapping of slides, so it could not be very clearly be presented how these Krylov methods and those TOD method which could not present, and this balanced truncation also, some overlapping of slides was there. So, but then we hope that at least something is there for you in this presentation. If time later on permits, then in these problem, in fact, what happens if we are able to solve one problem, then it makes listeners more familiar with the techniques. So earlier I was thinking of using chalkboard also, but unfortunately I could not get it here where I am. The net is not properly coming. So anyway, thank you so much for sitting there and listening to my presentation.
Thank you very much, sir. Still, it was very much elaborative. You actually gave insight to the model reaction to the participants, and also you discussed the various approaches, and you explored this model adoption area towards the in, to the participants, and also you discussed the future prospects. Those who are keen to work in this area, they might have got some ideas. So where they can explore the things, they can do some research, they can uh, get some work out of this talk. So thank you very much, sir.